But that doesn't make you what you were.
If this man is everything that you say he is, then the city needs me.
The city needs Bruce Wayne.
No, you can't. You're not. I'm whatever Gotham needs me to be.
Okay, so this is going to be an AP Physics C Mechanics review for the rotational motion FRQ. Reason I'm making this video is because our class failed the FRQ with a class average of a 58%. Now, instead of curving it, our teacher is offering us a retake. I don't know why there's not a problem with the 58%, but like Batman, I'm here to save the day. So I'm going to put the questions up on the screen instead of writing them out because they're pretty long titles. So for the first question, I'll have to draw it first. So, oops, So first question, we got this hill going down and we have a snowball on it, okay? So I need to label the forces, not components acting on the snowball. So what do we know about the snowball? We know that it's rolling. And how does something roll? As it moves down, friction acts on this portion. And imagine this is the surface. Friction acts on that portion. And if you remember the way friction works, it's in the opposite direction of the object's motion. So if the object is going down, the friction is going to be occurring from this point going up. And so now if we look at it on the circle itself, there's a force pulling the circle this way, but the circle itself is moving that way, which means the circle is going to rotate. So that's how the rotational motion is a force. So we know there's a force of friction on that, okay? So I'll write here force of friction. And now, so every force or every single object with a mass is going to have a force of their mass. So that'll come right from the center of the object, force, mass, and this exerts a force onto the plane it's on. And this is called a normal force. But this doesn't originate from the center of the object, it originates from where the object is hitting the surface. So let's draw it of likewise equal magnitude as force of mass, and we'll name this force of normal. So that's part A. So now let's clear all this up. Okay. And so now here is question 2. Calculate the linear acceleration of the snowball as it rolls down the inclined section of the roof. Now this part is very, very long. So what do we know first? Snowball is 250 grams. That's equivalent to 250 over 1,000 kilograms. Its radius is 4 centimeters, which is equivalent to, what, 100 centimeters in a meter? So 4 over 100 meters. And so let's do some trigonometry here. So there are two ways to solve this. This is the way I solved it. It's a little more difficult, but I view it as easier to understand. So this is the graphic we have here. And we know the distance off the ground of the snowball. So using the MGH formula, we have the mass 250 over 1,000 times G, which is 10, times H, which is 2 meters. And this will simplify to times 10 times 2 equal to 5 joules. So that means the snowball has 5 joules of potential energy in it before it starts rolling down the hill. So now we're going to need to find its kinetic energy at the end of the hill, and then using a formula that incorporates the final velocity of the final translational velocity, we'll be able to calculate the acceleration. So we can't just use 1/2 mv squared, because you'll notice that the ball rolls, which means it is losing some energy due to it being rotary. So let me grab out. Actually, I don't even need to grab out my formula. I've got it right here. So we know that it's 5 joules at the top. So we can set that to the left side. Oh, I'm on eraser mode. We can set that on the left side of our equation for the total kinetic or total energy in the system. So we can fill this equation in, but we don't know V, which is what we're trying to solve. So 1/2 times 250 over 1,000 times V squared. And we're going to have to do a plus because there's a rotary speed of the object. As the object spins, some of its energy is lost due to rotational motion. So this is going to be a similar formula. If you'll recall, let me grab out my physics textbook so I can give you guys the exact thing. And if you'll recall, here, and if you'll recall, rotational kinetic energy is, pencil mode, 1/2 times moment of inertia times W squared. I think W is actually called omega here, but I don't care. So we can interpret W squared as W is equal to V over R. This is because the translational velocity is equal to the radius times the angular velocity. So we can rewrite it as this. So now this formula becomes 1/2 times I times V over R squared. And we can easily solve for I because we have the mass of the object and the radius. I don't know how you would go by memorizing this. I was never taught to memorize, or I was never taught like a specific formula to memorizing it. I was just given a paper and told to memorize the important ones. So the moment of inertia for a sphere is 2/5 mr squared. So that we know these two variables, so we can plug that in for I. So now let's write this entire thing out with all of the variables plugged in, okay? So we have the 1/2 at the beginning, 1/2 times the moment of inertia, which is 2/5 times the mass, which we found up here, times 250 over 1,000 times the radius squared. Let me erase this over here so I get a little room to write. Sorry, guys. And times the radius squared, which is 4 over 100 squared. So that's the moment of inertia part completed. So now we need to multiply that by W squared. And if you remember, W is equal to V over R. So we don't know V, which is what we're trying to solve for. So we have V over R. And you remember R is 4 over 100 meters squared. 4 over 100 meters squared. So let's try to solve this without a calculator for a second. So when we apply the square to both of these, this will become 4 over 100 squared. This is already 4 over 100 squared. So these two easily cancel out. So now we're left with 5 equals, actually, no, I'll simplify this as well. 250 over 2,000 v squared plus 1/2 times 500 over 5,000 times v squared. So this is equal to 5 is equal to 250 over 2,000 v squared plus 500 over 10,000 v squared. This is 10,000 divided by 2,000 is equal to 5. Sorry, added an extra 0. So it'd be 250 times 5, which is equal to 1,250. So 1,250 v squared plus 500 v squared all over 10,000 is equal to 5. So that's 1750 v squared is equal to 50,123,000. V squared is equal to, so now I'm going to use a calculator. 50,000, that is 50,000, right? Divided by 1750. So now V squared is equal to 28.5714, dot, dot, dot. And then when we take the square root of both sides, we get V is equal to 5.34. I'll add in another one. This is the calculus truncating rule, 3 decimal points. So this is our linear velocity. That means whenever the ball, up in the top right, by the way, whenever the ball moves, the center of mass moving is going to move at 5.345 meters per second. I should probably put units on that. So let's erase all of this work, but keep that and this other essential information. So now, this is what we have. So now we can use this formula of v squared is equal to v sub naught squared plus 2 times a times delta x. But how do we find delta x? Well, guys, here they would give us a triangle of what the whole system looks like. So this we know as sine of 30, and you remember sine as opposite over hypotenuse equals 2 over x. Distribute x to both sides. Sine 30 times x equals 2. So x is equal to 2 divided by sine of 30. My people who have memorized the unit circle, you remember sine of 30 as 1/2. And so dividing by 1/2 is same as multiplying by the reciprocal, which is 2 times 2 over 1, which is equal to 4. So x is equal to 4. So the hypotenuse length is equal to 4. And the snowball moves across this length of 4 meters. So that's going to be our displacement x. And we already have the v. So now we have 5.345 squared is equal to 0 squared because the ball starts moving from rest, plus 2 times a times delta x, which is 4. So now 5.345 squared is going to be 28.5714 dot dot dot, and that's equal to 8a. So we divide by 8, and now we get a is equal to 3.57 meters per second squared. And this is the right answer. There's not another way to argue with that. Sorry. So that's from the Unit 5 Progress Check FRQ worksheet I was assigned for homework. This is not taken from a test. I cannot be rusticated for this. Just saying, this was a homework assignment. So, by the way, rusticated means like expelled, basically. So that's one of the problems done. So now let's move on to another problem. This is still recording, right? Yeah. So we've got this triangle, we've got a disc in it, we've got this arm sticking out, and then we have a load, and then we have a string attached to this wall, okay? And then this is at an angle. So we are given the information that a disc of a radius of 2 meters, which means this is 2 meters, and then the beam is 5 meters long. So we know that this whole thing is 5 meters long, and we're given this angle of 50 degrees. And the load has a mass of 12 kilograms, so 12 kilograms. Beam has a mass of 7 kilograms, 7 kilograms. Okay. So if you'll remember, the formula for torque is equal to radius times force times sine of theta. So what do we know here? We know the radius at 2 points. So the radius of the disk is equal to 2 meters. Radius of the beam is equal to 5 over 2 meters because that's the midway point of the beam. And the radius of load is equal to 5 meters because it's at the very edge. Now, in this case, you're not going to need to worry about the disk itself because the disk is not accounting for the tension in the string. The disk, in a weird way, the disk doesn't affect it being pulled down. So now let's do the math. So we have two torques that we know, the block and the beam. So I'll draw the system out right here. So you have the beam and then you have the block. So the beam is pulling down, or the block is pulling down. Is this the right pen? Yeah. The block is pulling down with 12 kilograms, which is equivalent to 120 newtons. And then this beam here is pulling down with 7 kilograms, which is equivalent to 70 newtons. So those are our two forces. So now the total tension in the string is equal to the torque of the load plus the torque of the beam. So now we can do tension in the string. Oh, I forgot. We also need to incorporate the radius of the, what's it called? The disk. So we'll cover that secondly. So I'll just put it, we'll solve that later. So, sorry. So the force, so of the load, it's at a radius of 5 meters from the center. So 5 times, and the force, remember we calculated it over here, is 120 newtons, and it's at an angle of 50 degrees, if you remember. And that's the angle from it being applied to the lever arm. So times sine of 50. And now that's going to be added to the radius of the other beam, which is 2.5 times the force pulling it down, which is 70, times sine of 50. And I'm gonna have to put this in my calculator. Oh, I'm in radians mode. So yeah, make sure you're in degrees mode when you're working with degrees, especially if you're taking calculus at the same time you're taking physics with calculus, I suppose. So this whole expression should eventually equal 593.684 newtons. And if you remember, the radius of the disk itself was 2 meters. And since this tension is being applied at a distance of 2 meters, but it's also applied directly on the, what's it called? It's directly applied at 90 degrees to the circle, remember? Because the tension is right here, so it's applied at a 90-degree angle. So now we can put this formula out as tension. Well, let's write it this way. So you remember this torque is equal to RF sine theta. Well, the string pulling it this way is putting a torque onto the circle. And we know that force to be 593.684 newtons because the torque is completely counteracting with the torque pulling the circle down. So they need to be completely equal. So let me erase the Newton symbol so I can work with more variables. So I need to set this equal to, so now the radius of the disk, you remember, was 2 meters. So that's 2 times the force of tension because that's what's being applied here, times sine of 90. Sine of 90 is 1, so tension is just equal to 593.684 over 2, which is simply equal to 296.842 newtons. And that should be your answer. Yes, that's what I have written down as well. So take a while to look at this, and we're going to move on to the final one. Okay, so I'm going to put this picture up on the screen for a moment, and I'm going to have to eventually draw it here. So we've got this giant beam, and we have a triangle here, and we have a rectangle around here. So we know the whole entire beam is 25 meters long. And we know that this distance is 5 meters, and we know that this distance is 7 meters, and we know that this distance is 11 meters. So what do we know so far? The beam has a mass of 50 kilograms. That means that the center of the beam is pulling down with 50 kilograms, and the box has a mass of 25 kilograms. So it's pulling down with a mass of 25 kilograms. 50 kilograms turns into 500 newtons. 25 kilograms turns into 250 newtons. So we have these two added together, which is 750 newtons going down. So that means these two blocks have to be exerting a force of 750 newtons up to counteract that and maintain equilibrium. So we can label this as force of 1 and force of 2. So 750, let me move this closer to the top. 750 is equal to force of 1 plus force of 2. So now we're going to solve this in relation with force of 2, because the one good thing my teacher taught me was that when you do these sort of problems, you want to set an axis of rotation. So we're going to set that to be f of 1. So that way we can completely negate f of 1 from this equation. So that means f of 2 is equal to 750 minus f of 1. Let me grab a drink of water. So that means all of our distances are going to have to be in relation from this point here. So we can sketch that out now. So we have the block over here, and then we have the other one here. So if this is our point, and this was 5 meters, and this guy was 11 meters from the end of the beam over here, then that's 25 minus 5, so now it's 20 meters away from the end there, and then it's minus 11, which is 9 meters away from there. So now we know one of the forces going down, which is going to be 9 times, because it's a force applied at 9 meters. If you remember, torque is equal to RF sine theta, and since these are going directly down or directly up, that's a sine of right angle, which is 1. So it's really just torque is equal to force times radius. So for the first one, we know the radius to be 9 meters, and you remember we calculated the force of this block to be 500 newtons. So that's going to be added to the force of the beam itself going down. So the beam itself was at 12.5 meters, so it's going to be also minus 5 meters because we're cutting off this 5 meters over here. So 7.5 meters plus 7.5 meters times 250 newtons going down, and minus, now we're going to need to incorporate force sub 2. So force sub 2 was operating at 7 meters away, so that's going to be 20 meters minus 7 meters, and you remember we got 20 from 25 minus 5, so 20 meters minus 7 meters equals 13 meters. So minus, and it's minus because it has to equal 0, minus 13 meters, and now if you remember we found force of 2 to equal 750 minus f of 1, 750 minus f of 1. And this all has to equal 0 because it's maintaining equilibrium. So let's expand this out. So 9, guys, sorry about that. I mixed up the masses of the block and the beam. That's my bad. So we're going to have to go back and retrace this one step right here. So it's not actually 500 newtons at 9 meters, but the two are swapped. Oopsie daisies, happens to the best of us. So it's 9 meters times 250 newtons going down, and then 7.5 meters times 500 newtons going down. My bad, guys. I didn't mean to lead you guys astray. So now we can erase all of this to get some more working space. And, oops. Let's move that up there. So now we can simplify this. So 9 times 250 plus 7.5 times 500, 6,000 minus 13 times 750 minus 9,750 plus 13 F1 equals 0. 6,000 minus 9,750 equals negative 3,750 plus 13 F1 equals 0. Now this is just basic algebra. 13 F1 is equal to 3,750. So divide both sides by 13. You'll get f of 1 is equal to around 288.461 newtons. So now using this, we can solve for f of 2, because f of 1 plus f of 2 equals 750. So now I know 288.461 plus f of 2 equals 750. So that means f of 2 has to equal 461.538 newtons. And that's the answer for that one. So that concludes the end of the review video. I hope this will help someone. It might be a little too late at night. Yeah. Batman operates in the dark anyways. Like and subscribe, and that's it. Thanks for watching.